Welcome back. In this video we will figure out how to use the nonlinear piecewise volt-amp relationship of diodes in nodal analysis. But first, let's start with a brief review of nodal analysis with resistors only. This will serve as a model for us to follow as we tackle the nonlinearities of the diode. Let's analyze this circuit to determine non-ground node voltages. We start, as we always do with nodal analysis, by adding node labels for the non-ground nodes and arbitrary current directions for the passive circuit elements. We write a KVL for each voltage supply and make up the difference to complete the system of equations with KCLs. In this case, we only need one at node B. We can add resistor voltages respecting the passive sign convention. The positive side of the voltage is on the tail of the current arrows, and the negative side of the voltage is at the tip. We then use Ohm's law to replace each resistor current with terms expressed with resistor voltages. The resistor voltage in the numerators can be replaced using simple KVLs. The node voltage on the positive side minus the node voltage on the negative side. These two equations form a linear system of equations that we can solve in a number of ways. One way would be to rewrite the system in matrix form and compute the solution. This is, of course, only possible since the system is linear. This matrix form of the system does not work for a circuit with a diode, such as this one. We start by notating the circuit in a similar fashion. Even though the diode is not passive, we label it with the positive voltage on the anode and the current respecting the passive sign convention. We write a KVL for the voltage supply, as we did before, and a KCL for node B. Now, the first term can be rewritten as we did for the previous problem, as it is the same resistor. The second term is where we run into the nonlinearity of the diode. We rewrite the second term by assuming a region of the volt-amp relationship. In this case, we've assumed the forward region. These two equations form a nonlinear system of equations that we have to solve to find the node voltages. This system is simple enough that we could simply use substitution. However, that will not be adequate as the circuit becomes larger. But we are lucky that we live in the future, and we can use a number of computer programs to solve this system. Here's some MATLAB code with some assumed values for the diode constants that calculates the solution for the system as the unknown node voltages. But be careful, these node voltages rely on the assumption that the diode is forward biased. We check this assumption by calculating the operating point of the diode. That includes the voltage across the diode and the current through the diode. Now, let's recall the plot of the volt-amp relationship for a diode from the previous video. If we plot the operating point, we can see that it resides in the interval for the forward biased region of the piecewise function. This indicates that the assumption led to a feasible solution. But that won't always be the case. There will be times where our intuition fails and we make an incorrect assumption. Let's use the same circuit, but make a different, incorrect assumption. We add the same notation and start off with the same KVL and KCL. Let's assume the diode is reverse biased. We can rewrite the resistor current as we have before, and in the reverse assumption case, we use 0 amps for the diode current. It's good practice to explicitly state the assumption. We'll need to check it again, so let's get that on paper here. These two equations form the system to be solved. In this case, it is linear, but why not abuse MATLAB just a little more? Using this code, we find these non-ground node voltages. Using these node voltages, we calculate the voltage across the diode. We've already assumed a value for the diode current, but I'll include it here just for completeness. Let's look at the plot again. and add the operating point as a big red dot. Here we see the calculated operating point does not reside in the reverse biased interval, indicating that the assumption is incorrect. This is just one way we can analyze this circuit, but there are others, each with their own advantages and disadvantages. We'll consider three methods. The first is to solve the nonlinear system directly using a computer, as we have in this video. We've covered that here, so let's cross it out. The next method is a graphical method called a load line. No computer needed for this one, but that comes with the inaccuracy of reading values from a plot. Finally, my preferred method, we make linear assumptions for each region. This will give us an approximate solution, but it's usually good enough. Also, in my opinion, this approach scales the best for more complicated circuits. With the first method done, let's move on to load lines in the next video. So stay tuned and good luck.